Okay, so let's go ahead and get started with our layer one overview. So the first thing we bring up here is actually the OSI model and how we encapsulate and decapsulate. So layer one, or the physical layer, this provides the means to transport the bits that make up the data link layer frame. So as we can see here, right, data link layer into the physical layer, and this provides the means to actually send all this data over to our destination. So this layer, the physical layer, is going to accept a complete frame from the data link layer and then encode it as a series of what we call signals. And we kind of have an example of these signals here. And then those signals are transmitted onto the local media. That local media being either fiber, it could be copper, it could also be Wi-Fi as well, wireless signals. And then those encoded bits, right, that are coming across that wire comprise a frame and are received by the end device or the destination and then de-encapsulated back into that application or user data. So if we take a look at the entire process, right, from source to destination, the entire encapsulation and de-encapsulation process, this is going to help us to understand the physical layer's role in getting data transmitted across the internet, right? So first we have our application data here, right? And then we have the transport layer, which is going to segment our user data. This is our transmission control protocol. Then that data is going to be placed into a network layer, which is a packet. And we're going to have our header here of our IP addressing. And then it's further encapsulated into a frame at the data link layer. And here we have our layer 2 header, layer 3 header here. And then that data link layer is going to be sent down to the physical layer, where it's going to encode the frames and create either the electrical, optical, or radio wave signals that are going to represent the bits in each frame. So again, we have the optical here, which is fiber or light, optical. Copper is going to be our electrical signal. And then Wi-Fi is going to be our radio waves or our radio frequencies. Okay? And then these signals are sent onto the media one at a time to the destination. And that destination's physical layer retrieves all these signals, right? So now we're sending it across one of our 3 transmission mediums, and then restores them to their bit representation, right? Physical layer is going to restore them to the bits and then send it up the OSI model back into that user data, okay? So the whole point of this slide really is to kind of show you the role the physical layer places. The physical layer is the last step in encapsulation to send your entire data across a transmission medium. Those mediums being fiber, copper, or Wi-Fi. Now moving on into our layer 1 overview. So what are the different physical medias that can transmit data? So we have copper, fiber, and Wi-Fi. So copper is going to send electrical signals. And these electrical signals are going to be how you determine the bit representation. So you see this top electrical signal here, right? That could represent a 1. This bottom one could represent a 0. Or the space in between, right here, could also represent a 1. So for copper, these electrical pulses, right, are going to have to match in between source and destination. What we mean by that is they have to read it the same, okay? So this computer here, its physical layer, or its NIC, and this computer here, let's say this is source, this is destination. They're going to have to agree that, oh, this long pause in the electrical signal equals a 1. Or this stop right here represents a 0. And we're going to get into who governs that, right? Who determines what organizations say, hey, you have to agree. Then we have fiber, and these are going to be patterns of light. So as you can see here, right, the light's strong here, and it gets a little weaker. So this may represent a 1. This may represent a 0. Then we have Wi-Fi. Okay, and this Wi-Fi is going to be patterns of microwave transmissions, or I like to call RF radio frequencies. So you can see here we have these sine waves, right? So think of a sine wave represented like on a chart, measured in hertz. And this sine wave has a couple points here that could represent a 1 or a 0. And we can modulate these frequencies differently, right? So here we have amplitude frequency modulation that represent our 1s and 0s. So we can see the amplitude is raising and lowering that frequency. So FM frequency modulation is going by the speed, right? How fast these sine waves are coming across. That can also determine the 1s and 0s. Okay, and then we have the governing organizations. So layer 1, because it's hardware, because it's physical, is actually going to be governed by like kind of hardware organizations or engineering organizations, right? So as we can see here, we're not going to spend too much time on this, but layer 1 is going to be governed by all these different engineering task force or governing organizations, like the IEEE, which we're going to hear about a lot in networking, right? Different IEEE standards. Whereas the TCP/IP stack and software standards are going to be governed by the Internet Engineering Task Force. So you kind of see in an OSI model here that layer 2 through 7 is going to be managed by IETF. And then layer 1 is going to be managed by all these different standards of engineering, right? Big one being the IEEE standards. Okay, now let's go over a little bit more in depth into layer 1 and how we encode and signal. So encoding or line encoding is just a method of converting a stream of data bits into a predefined code. Codes are just groupings of these bits, right? Let me get my pen out. Are just groupings of these, excuse me. Okay, let's get back to it. Encoding is just a grouping of these bits, right? Or a code, right? And these grouping of bits are used to provide a predictable pattern that can be recognized by both the sender and the receiver. So kind of what we're talking about, right? So encoding is just that pattern of voltage maybe sent across on a copper wire that is going to be used to represent zeros and ones, okay? Kind of like when we have that copper wire. Let me go back one slide so we can show you this. That encoding is going to say, okay, this section right here represented 101001, right? That's our encoding method, okay? And we have to agree on that on both sides of the link or the wire. And then when you decode, you take all those electrical pulses, right? And we're just using copper as an example, and turn it into something that we can recognize as humans. Because computers can talk in ones and zeros, but we have to make it human recognizable, right? And then we have signaling. So the physical layer, right, must generate the electrical, optical, or wireless signals that represent the 1 or the 0. So again, going back to like those electrical pulses, they have to represent the 1 and the 0. So the method of representing the bits is called a signaling method. So the physical layer standards must define what type of signal represents a 1 and what type of signal represents a 0. And again, this could be as simple as a change in level of electrical or optical pulse. So for example, a long pulse might represent a 1, whereas a short pulse may represent a 0. And as we can see here in this figure off to our right, we kind of represent this in different modulations for frequencies. So as you can see, we modulate this wave and we make it go a little slower here, a little faster here, and those can represent 1s or 0s. Okay, and now kind of getting away from the very deep fundamentals of layer 1. And again, if you guys have taken other CCNA courses, you may think, wow, this is going pretty deep into layer 1. You know, do I need to know this as a network admin nowadays? And to be truthful, it depends who you ask, but understanding these fundamentals can help you, right, in explaining, describing, and kind of conceptualizing the big picture, right? The entire OSI model. So yes, we go in a little deep, but now we're going to jump into stuff and vocabulary that you do need to know. And starting off, we're going to go over bandwidth. So bandwidth is just the capacity that a transmission medium has to carry data, right? And in bandwidth, notice we measure our bandwidth in bits per second, okay? Now, why is this important to understand? Because a lot of times people will say that they measure speed or bandwidth in bytes. Well, that is not true. We measure bandwidth and speed in bits per second. Because remember, a byte equals 8 bits. So 100 megabytes of speed is way different than 100 megabits in speed. I'm not going to do the math there, but times that by 8, right? So we measure in bits per second. Okay? So there's a combination of factors that can determine the bandwidth of a network, an entire network. Well, if we just keep it simple, right? And we have computer A here with a 1 gigabit per second link to this computer here, which is also 1 gigabits per second. That is going to be the bandwidth of this cable right here, okay? Saying we have the capacity to send a gigabit of data per second, right? Now, let's get into something that a lot of net engineers and network admins confuse, and that is throughput. So bandwidth is the capacity, right, of what is totally available. So if you look at our example here, we have this highway. And in this section of highway, we say that a total of 8 cars can come per second. Now, what actually happens, how many cars actually go on this road, is called throughput. So throughput is the actual measure of the transfer of bits across a media over a given period of time. So you may have 100 megabits of bandwidth per second, but because of multiple different factors, you may only get 70 megabits of throughput, actual data being transferred across that transmission medium. And this could be a number of different factors that affect your throughput compared to bandwidth. It could be your type of traffic, if you're getting a lot of like jumbo frames or a lot of fragmentation. It could be the amount of traffic coming from different nodes connected to that transmission medium, right? It could also be the latency. So a pretty drastic example of this, right, or an exaggerated one, is satellite communications. So my first job was a satellite communications specialist in the military. And we have what we call geosynchronous satellites orbiting Earth that are meant to transfer data from a transmission terminal and a receiving terminal from the ground, right? Antennas. These geosynchronous satellites will be 32,000 miles up in the sky, and there's an exact distance. I think it's something like 32,000 miles. Don't quote me on that, right? Well, in a satellite footprint, or this antenna may get a frequency that from your controllers that say, hey, you got 10 megabits of bandwidth. Well, transferring that signal 32,000 miles into the atmosphere with all that interruption or just that distance being sent, right? All that interference that could happen, you're probably not going to get your full capacity of bandwidth, because transferring a signal at 32,000 miles, you're going to cause a lot of latency. So the minimum latency for that far distance is 500 milliseconds. So your throughput may be something like 5 megabits per second. Okay, so a lot of different. When I was in the military, we used to joke about this all the time, that commanders wanted more bandwidth. And we're like, hey, that's not going to make that web page load faster, because you're always going to have that latency which affects the throughput, right? So 240 milliseconds transmit, 240 milliseconds receive, and that's just the best latency you could ever get on those transmissions. So kind of a drastic example of the difference between throughput and bandwidth. Okay, now going over a few more things of our layer 1 overview is EMI. And this is going to be part of our discussion, kind of jumping into the discussion of copper cable, right? Because still in today's LAN networks, copper media is still the most widely used, right? We use fiber a lot nowadays. That's more for our transport side of layer one. When I say transport, I mean long distances, right? But from layer two switch to the user, you still see a lot of Ethernet and copper media being used. So we got to understand what can interfere with that, and that is electromagnetic interference. So data that is transmitted on copper cables is electrical pulses. And with electrical pulses, these can be disrupted or deteriorated due to some sort of interference or really distance. So there is a distance on our Ethernet cables. I believe it's 100 yards, right? And if you go over that 100 yards, you're going to have something called attenuation, which is really just a deterioration of those electrical signals so that from source to destination, you lose something in there, right? Or you lose the strength of that electrical pulse. So the receiving node can't recreate those bits, right? So EMI is just any interference on a copper wire. Okay, now let's get into the different types of copper media. So there are going to be three main types of copper media used in networking. The big ones we're going to go over is UTP and STP. And then we're going to just touch on coax. These are just, your cables that you used growing up for cable, right? In Arizona, we grew up with Cox cable. We had coax coming into our house that provided our internet and the television, right? But what we're going to see in the enterprise and in network engineering is unshielded twisted pair and shielded twisted pair. Those are going to be the most common type of copper media we use. And these are going to be twisted into a standard here, right? See these twisted pairs? And we're going to make connections off these twisted pairs that give us the most bandwidth and distance for our copper media, okay? And we're going to get into that. So let's jump into the next slide. Okay, so let's go over unshielded twisted pair. So UTP is going to be the most common networking media, mainly because of the price, right? And this UTP cabling is going to be terminated by something we call RJ45 connectors, which allows the 8 pins to be crimped and connected into a Ethernet port, right? So UTP cable is going to consist of 4 pairs of color-coded wires that have been twisted together and encased in a plastic sheath. You kind of see right here is the copper, and then these color-coordinated plastic sheaths, right, that give it the copper cable some protection from minor physical damage. And then we have STP, which is shielded twisted pair. So you're going to have the same twisted pairs in there with the same color coordination, but what you're going to have is a lot more shielding for the actual copper cable. So you may have some foil shields here. You may have another foil shield that you'll have to cut off when you're actually doing your crimping. And then, of course, you have the jacket, which is something you also have a UTP. But STP is going to be a lot safer to use. And what do we mean by that, right? Is that STP cables have shielding to counter EMI, electromagnetic interference, and radio frequency interference. So we kind of have a more reliable signal, right, on STP, especially if you're working in an area where there's going to be power cables next to your Ethernet cables generating possibly that EMI. You're going to want to use shielded twisted pair. But of course, STP is going to cost a little bit more. So if you're in the procurement for your organization, something to think about, right? I know if you're working in the government, there's sometimes standards that your cabling, your layer one has to adhere to, especially if you're looking in secret or top secret environments. So now let's go over the different type of connectors for our copper media. So STP, UTP, it doesn't really matter, right? If it's if it's twisted pairs, you're going to use RJ45 connectors. Now I know it's a little blurry on the screen, but we can see our RJ45 connector here. And we can see that that's a bad connection because this jacket is kind of hanging off and you have exposed wires right there. Where if you can kind of tell here where we do the crimping in this little section here, the jacket is in there and it's going to crimp down on these wires and make that tight connection, right? So we don't have loose pins like we do in this bad connection here, okay? All right, now let's go over the different connection and cabling standards, right? So we can see here that we have two standards on how we make the pin layouts when we're creating cable and crimping down our RJ45 connections. So we have T568 Alpha and T568 Bravo. And you can see here that we have these 1 and 2 pairs will be the same color. And then this pair 3 and 6 will be the same colors as well, right? So why am I pointing this out? Because in typical Ethernet or fast Ethernet, these pins right here, 1 and 2, are going to be used for transmit. And then pair 2 here, which is going to be pins 3 and 6, are going to be used for receive. And this is going to be what we call an Ethernet straight through when both sides have the same cabling standard, okay? So if both sides are T568 alpha, then they're going to be a straight through. A crossover is when one side is going to be T568 alpha and the other side is T568 bravo. Now, why would we do this? Because in the days of old, if we were connecting like devices or similar devices, so router to router, we needed a crossover cable, right? And that has to do with the pinouts, because we couldn't be transmitting and receiving on both sides on the same pins. But nowadays, we have technology and software that fixes that. It's called MDIX. And you won't be tested on this, but it's good to know that if you're working with legacy equipment, you're trying to connect up switches to each other, and you're not getting anything, and they're, let's say, switches from the early mid-2000s, you may need to use a crossover cable, because back in the day, similar devices needed a crossover to be able to communicate. Now, the last one we're going to talk about is a rollover cable. This is going to be your console cable, right? This is a Cisco proprietary standard that you use to console in to Cisco routers and switches. It's that blue cable that we should all be familiar with. Okay, and then again, just another slide to kind of go over the different standards, right? We call these the TIA standards. That's another one of those governing organizations for layer 1. So where I worked in the government, we used this standard, T568 Bravo. So that's always what I was used to making cables with, especially when I was new, right? It's always important for the new guys to make the cables, right? Your junior network admins, if you just have reels and reels of cables and you're plugging in a new office, you got to make them grab those crimpers, right? So we have 1 and 2 as transmit, 3 and 6 as receive. Okay, and then the last thing we're going to go over is the 802.3 standards, and this is the Ethernet standards for Ethernet technologies, right? These are the different CAT categories. Well, CAT stands for categories, right? So we have Cat 5e, Cat 6, Cat 6a, and Cat 8, and there is like Cat 7, but these are their different categories that define the bandwidth or the speed that's available for these copper mediums. And this is going to be described in the 802.3 IEEE standard. Remember, this is another one of those governing organizations for layer 1. So as you can see here, the differences between these CATs, these categories. So we have the standards, 1G base T stands for 1 gigabit of bandwidth. Then you see Cat 8 goes all the way up to 40. Cat 6 alpha can provide 10 gigabits standard of bandwidth. And you can see they're all using RJ45 connector types. Okay, so that's going to be it for this first section. I don't want to make this video an hour long. So when we come back, guys, or in our part 2 video, we're going to go over different errors that can occur on our copper media or our Ethernet. So please stay tuned, and thank you for viewing.